Welcome to the course on two-dimensional signal processing, principles and practices. In the previous lecture, we have done the 1D FIR filter design using the window method. In this lecture, we will see the design of the 2D FIR filters, different methods, and use this window method. What is the design procedure for it, and what are the 2D windows as we know the 1D window. I will continue with this 2D filter design. That is FIR, especially the 2D digital filters, the usage, how these are all done, the design procedure, what is the usage of this 2D digital filters. As the case of the 1D digital filter, it is going to be retaining some frequency components, and then if the sum of the band of frequencies or to be removed from the response or the frequency response of the digital filters. That's the purpose of designing the filter. Just removing the frequency component may be here in the two-dimensional signals, it may be a noise that's going to be in the various form into the image. So the basic usage that first to design it is we have this one is you have the filter specification. That's the for most important case of designing the filter. So the filter specification is the one we need to know either in the time domain or in the frequency domain. So in the case of here especially it is known as a frequency domain details. So knowing the filter specification, and we proceed with the filter design. So the filter design in the sense as we did in the 1D case, finding the coefficients of the filter. The digital filter, especially the impulse response h of n1, n2 in the case of 2D, or the frequency response h of z1, z2, or it can be h of omega 1, omega 2 as a Fourier transform of that. So also these details can be done, or we can get these values in the process of filter design. And after designing the filter, this needs to be realized either in the DSP or in the FPGA. So the implementation of this, the coefficients or the Fourier transform or the Z transform of the filter which is designed is the third step. This is how the filters are being used. This is especially for the digital filter. So the case of considering the digital filter, the class of digital filters, we take this impulse response for the discussion h of n1, n2 is real, because the realizable ones now and the practice or the real one. And if it is real, then it is also to be stable. So the stable response or the stable filter which will have the impulse response absolutely sum. So in 2D also this is valid. In the 1D case also the impulse response h of n is absolutely summable for the summation varying from n 0 to infinity or minus infinity to plus infinity. Here this is stable for the two dimension. The absolute of h of n1, n2 is less than infinity for the summations minus infinity to plus infinity of n1 and n2. So these two requirements we have it for the discussion, so that the practical filters can be designed based on that. So taking the FIR filter, which is linear phase, we had seen that midpoint symmetric, midpoint antisymmetric cases of type 1, type 2, type 3 and type 4 filters, how the coefficients spread in the impulse response. Actually h of n is having the coefficients, that is midpoint symmetric or midpoint antisymmetric. In that case what are the length of the coefficients depends on that. We did in 4 types of filters. So that's offering the linear phase characteristics of the FIR filter. Here in 2D we call this as either a zero phase or a linear phase filter. So the digital filter is said to be zero phase. If it has, then the frequency response is a real function. H of omega 1, omega 2 is a real function done. And in that way h of omega 1, omega 2 is a h asterisk omega 1, omega 2. That is this is coming from the symmetricity property actually. So if the same thing if we extend to the impulse coefficients or the impulse response of the filter, h of n1, n2 is h star minus n1, minus n2. So this is from the straight away from the Fourier transform and the symmetry property of it. So if we have this symmetry property in the coefficients, what is the advantage of having this design? So the thing is, in h of n, if you take the 1D case, that the midpoint symmetric in the sense if you have n by 2 coefficients redundant, the other n by 2 coefficients, so then the number of coefficients to be decided or estimated is reduced if it is symmetric, or if it is symmetric, then we also have the advantage of having the phase response is linear phase. So having the symmetric property of the filter h of n1 comma n2, say star minus n1 minus n2, the conjugate, if it is real, then this is going to be simply h of minus n1 minus n2. So this is applicable only if it is complex number. So the reality, we consider all these coefficients to be real. So h of n1 comma n2 is equal to h of minus n1 comma minus n2. So this is one kind of symmetricity which is offering the linear phase for the filter response. So now this is also symmetric with respect to origin. Origin is here is a 0 comma 0. So now considering the importance of this zero phase or linear phase filter. So FIR filters are linear phase or zero phase. In this case, the characteristics of this filter is if you apply this FIR filter to an image or the 2D signal, in this case, that it doesn't distort the frequency components. So it would pass this amplitude as such, and the phase is having there is no distortion due to the phase characteristics. And whereas if it is non-zero or the non-linear phase filter, it's definitely distort the frequency components if it is applied to the image. So this point needs to be noted, the frequency components to be retained or the distortion to be avoided, then the filter characteristics to be linear phase or the zero phase. So the zero phase is easy to achieve in the FIR filters, like the case of it is simplifying the number of coefficients estimation. So that the design and implementation also is becoming easy in the case of zero phase the linear phase filters. So the zero phase impulse response, let us take this as h of n1 comma n2 for the filter, and then the frequency response is h of omega 1 comma omega 2. Now we know how do we obtain this h of omega 1 comma omega 2 for the given h of n1 comma n2. So the impulse response and the frequency response, the Fourier transform of this will get the frequency response. So for these two things, that how do we get this h of omega 1 comma omega 2 is nothing but applying the Fourier DSFT here. So in the spatial domain, we call that as a DSFT, discrete space Fourier transform. So h of n1 comma n2 e power minus j omega n1 and j omega 2 n2. This omega 1 and omega 2 are the frequencies of this we need to find. So here h of omega 1 and omega 2 function, the real function needs to be found for this. So this is having the region of support RH. So n1 and n2 belong to RH, is the H has the region of support. So H of n1 comma n2 is defined in the two-dimensional n1 and n2. There is a certain region of support, that's a finite extent sequence. Suppose in this case that RH is known. So this RH can be split into three categories, whereas for the frequency response, this n1 n2 comma only for the origin, that is equal to 0 comma 0, n1 n2 0 0. So this results in h of n1 comma n2 is 0 0, and R the remaining cases n1 n2 is belonging to RH dash, which is this is one case, and H double dash, which is the another. So this particular equation can be split into three components. One is origin, and another one here, this is the h of which has a h of RH dash and RH double dash. So what are these RH dash and the RH double dash region of supports of the sequence? So here these regions are mutually exclusive, 0 0 separately, and this region of support is also separate, and the third one as a region of support RH double dash. So what are the RH dash and RH double dash? If we take the RH dash is belonging to the region of support of h of n1 comma n2, where n1 and n2 values having the region, not the positive one. And the second category RH double dash is h of n1 minus n2. So this is the case where if you substitute n1 and n2 are negative, so that is the portion of the sequence in the 2D or the impulse response contributing to the RH double dash. So this is split into three parts. One is 0 0 and the positive part of it, and then h of minus n1 and minus n2. So using the symmetricity property of this, h of n1 comma n2 is equal to this h of minus n1 minus n2. So if we then if we can combine this in a one region of support, that is n1 n2 RH dash only, as if this is equal, then it is going to be the summation 2 of h of n1 comma n2, that is we can take it out, and here e power minus j omega n1 and e power plus j omega n1. So these and e power minus j omega to n2 and e power plus j omega to n2, these two contribute the cosine function. So the cos of 2 cos omega 1 n1 plus this cos omega 2 n2, we can simplify this to get the cosine function. So the frequency response is a summation of linear combination of, that is cosine of the omega 1 n1 and omega 2 n2. So with by separating only the origin sequence plus this sequence h of n1 comma n2 is a linear combination of this summations would result in the frequency response. So what we can do, the FIR filter can be expressed as a linear combination of cosine terms. So these cosine terms represent that this is the real filter. So the FIR filters are the real filters here, and that is coming from the property of the symmetricity h of n1 comma n2 is equal to h of minus n1 comma minus n2. And this is one fold symmetry. So we can see the remaining symmetries as well. So we take the example of the h of omega 1 comma omega 2 frequency response. How do we find? And we have done this already, but to recall the surface plot, how this would like it look like, and then the surface of low pass or high pass filters. We just bring this example over here. So determine this h of omega 1 omega 2 for the given impulse response. So this is a 2D sequence which has 1 by 3 at the origin and 1 comma 0 as 1 by 6, and then 0 comma 1 as 1 by 6, and here again 0 comma minus 1 as 1 by 6, and then minus 1 comma 0 has 1 by 6. So these values are 1 by 6. So to find the frequency response for this 2D sequence, so what we do is n1 is varying from, take the minus infinity to plus infinity, n2 also, and this is the equation of DSFT, where minus j omega 1 n1 and minus j omega 2 n2. So the case what we can say is identifying this is 0 comma 0 is 1 by 3, and these two terms would become 0, and 1 by 6 we have this all over these 4 points, that is 1 0 and then 0 1 minus 1 comma 0 and then 0 comma minus 1. All these values will give the 1 by 6. So 0 from that we get omega 1. Suppose this is 1 0, we get e power j minus j omega 1, and if it is going to be minus 1, this n1 is minus 1 and this is 0, so we get this one, and similarly the other 4 combinations we have here 1 2 3 4. So these are also, if we simplify this, these two terms will form a cos and this is cos. So we can see that this frequency response is the linear combination of the cosine inputs, which is for the real filter. So the h of n are all real values. So that's the h of omega 1 comma omega 2. So from this can be further simplified to have 1 by 3 into 1 plus cos omega 1 plus cos omega 2. So this is the equation of the filter, which has the frequency response and a linear combination of cosine terms. So if you plot it with the frequency response with the mesh plot or the surface plot, you can get that omega 1 variation and omega 2 variation. You can see this is a high low pass filter. You can have the case of surface changing here. This is a case of the surface plot of the low pass filter, which is representing cos omega 1, cos omega 2. So the kernel, the filter which we had taken is the just to visualize the 2D frequency response of a filter, low pass. And the similar thing can be obtained for high pass as well. That is also going to be a linear combination of cosine functions. So now taking the symmetricity property. So we had the coefficients which were, if you see that in this example, we had the coefficients, this are equal, right? So what is the symmetricity property which is used in the case of generally the design? So the case if it is symmetric with respect to origin, so the half of the points h of n1 comma n2 are independent. That means it is sufficient to have estimate only the half of the h of n1 comma n2, not the entire one. So in case of the twofold symmetry, like we had in the midpoint antisymmetric cases, so there are a few symmetricity used in the 2D linear phase filters of FIR. That is 2D, the twofold symmetry here. So h of n1 comma n2, the coefficients will be equal to h of minus n1 minus n2. So we'll see the example of this in moment. So 1 1, suppose n1 1 1. So this would have h of minus 1 and minus 1. 1 1 will have that is twofold, folding it like with respect to the origin, we fold it this way, minus 1 1 and minus n2 are this way. This is only having the equal one of for n1 and minus n1 n2 minus n2. So there can be coefficients to further simplify the estimation of the filter coefficients, that is for the fourfold symmetry. In that case, h of n1 comma n2 is equal to h of minus n1 comma n2, also h of n1 comma minus n2. So if all these coefficients are equal, then further simplification of the estimation of the coefficient can be achieved, and in also the linear phase. So the corresponding Fourier transform, if we take the Fourier transform of this, h of omega 1 comma omega 2 is equal to h of minus omega 1 and minus omega 2. So whereas for this case, the Fourier transform is h of omega 1 comma omega 2 equal to h of minus omega 1 omega 2, this case, and here h of omega 1 minus omega 2. So the negative sign is given in this case. So this is for the Fourier transform of the fourfold symmetry. And if it is eightfold symmetry, so you can take a square paper and then fold it twice, or fold it 4 times and fold it 8 times. So these are the where this surface matches, those points are same. So here it's eightfold symmetry, h of n1 comma n2, h of minus n1 comma n2, h of n1 comma minus n2. This is the fourfold symmetry. Apart from that, it is if you just interchange n1 and n2, that would also be equal. So h of n2 comma n1, the axis change n1 and 2 is making n2 n1. So this is eightfold symmetry. So now if for the Fourier transform, h of omega 2 comma omega 1 is equal to h of omega 1 comma omega 2. If we interchange these two, still the real function is the same. So the intermediate, this omega 1 is with a negative and omega 2 negative also equal. So this is eightfold symmetry. This further simplifies the coefficients needs to be obtained for the design. So the twofold symmetry, as we said, h of n1 comma n2 is h of minus n1 comma minus n2. The cases, you can see these are the independent terms. So these independent terms will be reflected here. If you just fold it or this way or this way, if you fold it this way, these points will be equal here. If you fold it this way, then with respect to these points will be equal. So this is the case of, at least I have for 3 by 3, you have 4 independent terms to be estimated in the filter design if it has twofold symmetry. And in the fourfold symmetry, which can be again the condition we had seen, that h of n1 comma n2 is minus n1 and n2, or n1 comma minus n2. So in this case, you can have the 4 folds, 1 2 3, this 4 folds. So if these are the sample points of h of n1 comma n2, and these are the independent terms. So these are dependent terms, like if you fold it, you would get these terms. If you fold like this, you will get, if you fold like this would be obtained, and this way also. So there is a fourfold symmetry, 1 2 3 and 4. So this fourfold symmetry case have only 4 independent terms for the 3 by 3 one. And if we have the eightfold symmetry similarly, so in that case, it is further simplifying the coefficients, like only 3 samples of the h of n1 n2 to be known, and the remaining can be obtained. So it can be of this way, and this way, here, and all the ways it is possible to have the 8 point, that is eightfold one. So this includes h of n1 comma n2 is varying, or it is equal to h of n2 comma n1. So this condition is the additional one which gives the eightfold symmetry of folding it this way, folding it among this in one quadrant only, 2 3 and 4, and then you can have all the symmetries of the previous one also counted in it. Apart from that, this is only having the 3 independent terms for the 3 by 3 case. So we can see that if we find only 2 3 terms, then the remaining terms are known for this h of n1 comma n2. region of support in this case. So this symmetricity property helps in the easiest way of number of coefficients estimation, which is less for the design. So it imposes this if we impose the symmetry constraints, it reduces the number of independent parameters, and it must be estimated in the design. So we have this FIR filter specification. So the three steps which we use generally is the filter specification, and then we proceed with the design, and then the implementation. So the first part is let's get to know the filter specification, in which the 2D filters are generally specified in the frequency domain. Then we had also seen in the case of 1D FIR filter design for the window method, HD of e power j omega, that is given, that is ideal low pass filter for the case. And similarly in the 2D also, what is the specification is known in the frequency domain. So h of omega 1 omega 2, which is equal to omega 1 plus 2 pi and omega 1 comma omega 2 plus 2 pi. So this is equal, should be known for all omega 1 and omega 2. Okay. That means with respect to omega 2 pi, the periodicity you can note it down in the frequency domain plus 2 pi, and this is plus 2 pi here. So both omega 1 and omega 2 direction. And if we just take this omega 1 from minus pi to plus pi for the h of omega 1 omega 2 and omega 2 minus pi to plus pi, it completely specifies this frequency response. So it is sufficient to have only this portion. So if we plot it, the frequency response, actually it will have some, depends on the filter characteristics, you will have this this is a contour plot, omega 1 and omega 2, where it is minus pi to plus pi, and it is showing the, this is actually the omega 2 here, okay, omega 2, and this gives the intensity of the h of omega 1 omega 2. So that is here. So the scale of omega 2 is this, and then h of omega 1 omega 2 is giving the amplitudes, that is having the different colors of this intensity. So we can have omega 1 and omega 2 varying, and the h of omega 1 omega 2, which is a function of omega 1 and omega 2, can be specified between minus pi to plus pi, and for both omega 1 and omega 2. Now getting the filter responses like low pass filter or the band pass or the high pass filter, these kind of filters, what is the filter response possible in case of 2D? So in 1D it is simply low pass, high pass filter, and the band pass filters and band reject filter, all pass filter, and so on. So whereas the filter response here in 2D is defined in two different ways. That is, one is the separable low pass filter response, another one is circularly symmetric low pass filter response. So the filter response is separable, or filter response is circularly symmetric. Okay, so what is the meaning of this separable low pass filter? We'll see that one thing we can get that is separable filters, which is also related to the separability concept. So h of omega 1 comma omega 2 is we can write it as h of omega 1, h1 of omega 1, h2 of omega 2. That is a product of two sequences in frequency domain, that is continuous here, it is not discrete. Okay, so the h of omega 1 omega 2 is equal to 1, that if it is separable response for omega 1 less than the cutoff frequency of omega c1, and omega 2 that is less than or equal to the cutoff frequencies at the omega 2 direction, omega and omega 2 direction, and it is 1. Whereas for between omega c1, the cutoff frequency to pi, and the cutoff frequency to pi, this is 0. So it is 1, like what we say in the case of low pass filter, ideal low pass filter in the case of 1D. It is similar to that here in 2D. The same thing is where in h of omega equal to omega less than or equal to omega c, where this is 1 and it is 0 otherwise. So the same thing which is extended here in 2D, the response is case. Here one thing is separable, that means its impulse response as inverse Fourier transform of it, DSFT inverse h of n1 comma n2, can be written in terms of product of two sequences, h of n1 and h of n2, or you can say h1 and h2 as well. So this is the separability concept, which is equal to here sinc function. So h1 of n1 is one sinc function, and h2 or the h of n1 n2 here, and this is h of n2. So these two products is equal to the h of n1 comma N2. So this is separable. The impulse response is separable. So equivalently in the DSFT also this is separable, H of omega 1 into omega 2. So what is this is called the frequency response which is the low pass filter has, which is separable. So that is 2D separable low pass filter response. That is what we said is H of omega is H of omega 1 into H of omega 2. So if you look at the response, to visualize the H of omega 1 omega 2, where omega 1 and omega 2 are these things, the axis is given, and you see that this is the filter response in which we have this A that is equal to omega c1, the cutoff frequency here, that is in omega 1 direction where it is 1, and omega c2 which is B here for this. So if you take as a 2 1D filter responses, so this is one having H1 omega 1 and this is H2 omega 2 as we said. So here A is the omega c1 and that's from minus pi to plus pi. So A is minus omega c1. This is a low pass filter in H1 omega 1 dimensional, and again this is another one dimensional filter response which is H2 omega 2, which has omega c2 and this is omega minus omega c2. So here from minus pi to plus pi. So now if we take the combination of the product of these two, so 1 here and this would also give 1. So these 4 regions would be having the 1 and the remaining this portion would have as 0. So here omega c1 greater than, those values are 0. Here similarly this 0 and this 0. So this is the separable filter response, so which is for the low pass filter. So if you take the H of omega 1 omega 2, this is what is the 3D view of it, omega 1 and omega 2, H of omega 1 omega 2, the response we can see over here, the frequency response is plotted. So this is the same thing, like if you look at the top view of it, this is the response and here is the 3D response of it, so which is having the 0 and 0 here, that center, and here it is 0 and here it is 0, omega 1 omega 2. So this is a 2D separable low pass filter response, that's frequency response. And if we have this filter impulse response, what is the impulse response of it? So if you have this rectangular function, you know that is going to give the sinc function, right? So we see this impulse response in both the directions. If it is separable, so this is one sinc function and this is another one. So we can even say that this is the impulse response of the 2D separable filter, that H of omega 1 omega 2. If we take the case of inverse DSFT, then we can obtain this one, and it is plotted as a mesh plot or the surface plot here, so with to represent this in 3D. So this is a 2D separable filter impulse response. So you can see the at n into 0, this is giving the high value, and the separable filter, the ripples are the sinc function which is having here, giving the ripples over in the center. You can see the center having the ripples, not these portions. So now taking if the filter response is circularly symmetric, that is the second category, same low pass filter, if it is circularly symmetric, what should be the function H of omega 1 omega 2? So there are these two types the filter responses can have. These two types, even windows also can have the responses. So it is 1 for omega 1 square plus omega t2 square root is less than omega c. So omega c is only one cutoff frequency here, which is having the circular pattern, that is omega n square plus omega 2 square root is omega c, and it is above omega c, this value becomes 0. So that is from omega 1 less than pi and omega 2 less than pi. So, the impulse response of this H of n1 comma n2, if we take this omega c by 2 pi and root of n1 square n2 square, so it's a function of n1 square plus n2 square, we should note that. And similarly this is related to the omega 1 square plus omega 2 square, and J1 omega c is the cutoff frequency n1 square plus n2 square root. So J1 is corresponding to the Bessel function. So J1x is the Bessel function here. So we'll see the J1x pattern. So J1x by x is that pattern which we had. This is the Bessel function of our x. And so circularly symmetric filters having the impulse response which is of the Bessel function. Also we can have the h of omega 1 comma omega 2 is the cutoff frequency, omega c, which is having the circular pattern, and unlike the low pass filter of the separable one, which is having the squared pattern. Okay. So pi to minus pi in this region, all these regions, it is 0, and here it is 1 at the maximum in this case, h of omega 1 comma omega 2. So this is circularly symmetric low pass filter. And the circularly symmetric low pass filter is h of, if you visualize this is the same thing as a top view. So in the 3D, we can visualize this is omega 1, omega 2, we will have this pattern, a circularly symmetric response. And if you have the impulse response of it, you can see the Bessel function, the circular h of n1 comma n2, which is having the circular patterns in all these regions. Okay, so and it has when it is 0 0, you have the peak response, whereas in case of separable window, it has in the only at the n1 0, n2 0 values, it has the ripples. So here it is not this, the ripple will have the circular pattern in the case of circularly symmetric filters. So the thing of taking the ideal circularly symmetric ones, so if we had seen this is the portion of it from minus pi to plus pi. So this is going to be anywhere repeating in the 2D, omega 1 and omega 2 response. So the same response would be repeated with respect to 2 pi, and the same response will be repeated with respect to minus 2 pi for omega 2. Similarly, omega 1 as well, this would be repeated, plus 2 pi and minus 2 pi. So this is repeated, and it is sufficient to have the response, study the details or the design around this minus pi to plus pi and minus pi to plus pi. That's why we said that this h of omega 1 omega 2 would be fully defined in this region, minus pi to plus pi and minus pi to plus pi. This is the frequency response of the circularly symmetric filter. So with this, we had seen the introduction of these 2D digital filters, especially the FIR filters, and its symmetricity property, 2-fold, 4-fold, and 8-fold symmetry, in which how it is reducing the design parameters or estimating the h of n1 comma n2, the coefficients or the number of independent terms gets reduced to using the symmetricity property, which helps in the linear phase or zero phase FIR filter design. Also introduce these filter responses can be of two types. One is this separable filter response and the circularly symmetric filter response. So this is in the case of 2D. The same kind of separable and circularly symmetric cases for windows also can be visualized, and what is the corresponding window expressions, what we had seen in the frequency response expression and impulse response expressions of the separable and circularly symmetric one is also applicable to the window functions. So if a window is separable window or the circularly symmetric window, so then same responses can be Fourier transform can be obtained for it, and the impulse responses can be obtained for this window functions. So we'll see those different window details in the design of the FIR filter in the next lecture. Thank you.